All right. So we're given a problem, and we're asked what is the equation in Cartesian, which is rectangular, coordinates, equivalent to the polar equation. And our polar equation is r equals 9 cotangent theta times cosecant theta. Now, before we start, I wrote down here to the side what you see here, and this is a little bit of the relationship between Cartesian and polar coordinates. And we're not going to need to use anything more than these four. In fact, we're primarily going to just use two for this video. So we know y is r times the sine of theta. We know x is r times the cosine theta. We know r squared equals x squared plus y squared. And tan theta equals y over x. Now, this one may be a little unique. You might not have seen this one before, and that's fine. I'll show you why tan theta equals y over x real quick. Well, what's y over x? Y, that's an ugly y. Y over x equals r sine theta over r cosine theta. Now our r's cancel. We're left with y over x equals sine theta over cosine theta. And y over x, or sine theta over cosine theta, equals tan theta from just your trig identity there. Okay, so, and the reason why I wanted you to know what that is for sure and why that is because we're going to use that relationship tan theta equals y over x in solving the problem. So I'll write a problem. The problem was r equals 9 cotangent theta times cosecant theta. All right, so before I start, what I'm going to do is I'm going to use two trig identities so I can get rid of code. I don't like working with cotangent and cosecant. Other people might, but I don't. So I'm going to get rid of these two terms. And I look at a table of identities that I just pulled off of Google Images. Cotangent theta is 1 over tan theta, and cosecant theta is 1 over sine theta. So I'm just going to plug those in to what we already have here. So r equals 9 times cotangent theta, but that's also 1 over tan theta times cosecant theta, but that is also 1 over sine theta. All right, then when we combine the terms, we have r equals 9 over tan theta times sine theta. Now what I'm going to do is I'm going to multiply both sides by tan theta sine theta, and then I get r sine theta tan theta equals 9. And you see what I did? I just, again, multiplied both sides by tan theta sine theta. This canceled out, and I had a tan theta sine theta on that end. And now I'm left with something I can put in terms of x and y. R sine theta, well, what's r sine theta? We look up here. R sine theta is y. Tan theta is y over x. So already we have our equation in terms of x and y in terms of Cartesian coordinates. So let's write it all out. R sine theta goes to y. This goes to y. This goes to y over x. So we get y, ignore that. We get y times y over x, all equal to 9. Which in turn is y squared over x equals 9, which in turn equals y squared y squared equals 9x. And if we want our equation to equal 0, we just got to subtract one of the sides from both sides. So what I'm going to do is I'm going to subtract 9x from both sides, and this goes to 0. And then I have on the left side, I have y squared minus 9x equals 0. And that right there is the answer to this problem here. And I'll write it out. It's y squared, I'm going to try it, minus 9x equals 0. All right, so that's, we'll call part 1. Part 2 is which of the following curves is associated with the equation given above. Which of the following curves is associated with the equation given above? We have our choices: a line, a circle, a parabola, and a hyperbola. So what I do to answer these is I put it in a form that I can easily recognize. So let's get our 9x back on the other side. So we have y squared equals 9x. And let's solve for y. You could look at it and solve for x, and you could realize that if you use x as a function of y, and you recognize it that way, that's fine too. But for me, I like to put everything in terms of y. And if we do that, we take the square root of both sides. So square root of this side, square root of this side, and we're left with y equals, and this is a key component to this problem, y equals plus or minus 3 square root of x. Because square root of 9 is 3, and square root of x is square root of x. And you can see that makes sense, because if I squared this, whether it's negative or positive, will still give me a positive y, as we've defined in our equation. So now I see this, and you could do a couple things with this. You can plug it into your calculator. You could just start graphing different points on this, or you could plug it into your calculator. And the way you would plug it into your calculator is you would set one of your y equals to 3 square root x, and the other one equals y equals negative 3 square root x. And if you don't know this already, plug it in, see what it looks like, and what you'll get is a parabola. And this is positive square root of x. This is negative, and this is Mathematica that I'm using to show you this. And this is negative square root of x. And it was hard for me to get the window size right, but this is the same graph as this top one. And this graph here is the polar plot of our original equation, which you see it's a parabola extending in the positive x direction. And this is a graph of the function we came to. And this is a parabola extending to the x direction. Their values are the same, even though it might not look like it. But this is a confirmation of the answer. So again, that should be the answer to both those. Yep, so we got our y squared minus 9x equals 0. And which of the following curves is associated with the equation given above? Well, it's a parabola.